So today we will continue on from our lecture on Monday into the concept of virtual memory. The beginning. So let me quickly warn you for those of you who take my system skill and file processing class. Again, there's some of this will be similar, some of them will be new. At the end of this class, I'm going to then talk about some of the things that Linux is using that you can enable, but right now I don't recommend you to enable it because it's not great yet. It's still, we as researcher, including myself, are trying to figure out how to enable some of these techniques in a way that is faster. But the majority of today's discussion will be on virtual memory. And this is a really, really old concept. Uh, how many of you used Windows 98 before? Oh, it's not too old. It's not like my generation. It's not your generation. What's the first version of Windows that you used? XP. Okay. Wow, I feel old. Have you heard of Windows 3.1? Okay, yeah. So there was a time where you need when you boot up the desktop, everything would like the MS DOS comes in, and then there's a menu that you can select, and one of them would be Windows 3.1. When you boot it up, it's the old version of Microsoft Windows. You have Paint. I think you have Solitaire, and I think you might have like a really ancient version of like Microsoft Word. But I think that run on MS-DOS, not even on Windows. So so back in the day, the virtual memory, the concept of virtual memory is not exactly like widely used yet. But when we move on to like Windows 95 and then 98 and then I forgot what the next one is because it's kind of like bad for people who don't use it, and then XP comes next. I think it's called Windows SE or something. It's like a Millennium, like 2 year 2000 version. And at some point there'll be a configuration that you can configure and say how much virtual memory do you want on your machine. And we'll talk about what is virtual memory today. How does it translate to like things like cloud environment or if you want to use the GPU, right? So let me test it. Make sure I can draw. Okay. All right. So the first question you might have been wondering is why the heck do I have to learn this? Why do I even care about virtual memory, right? So generally, as I said last week, day, you want something like I want unlimited memory. I want to be able to only think about allocation happening in my program. I don't want to worry about anyone else's pointer. Right? That alone is giving me enough seg fault to the point that you can go crazy. So I don't want to worry about someone else's pointer. You also want the memory protection. What do I mean by that? Basically, let's say you run 10 applications in parallel. You want to make sure the third application cannot access the data of whatever I'm writing right now, right? Otherwise, something is leaking, someone's hacking your machine, and that's not safe. Virtual memory provides all these things. So what exactly is virtual? Basically, when you have an address, they're associated with one unique location in your DRAM. This location is called the physical address. When you are running your application, all the pointer that you have are virtual address, actually. Everything down to the assembly code, that address is virtual address. There is a mapping between the virtual address to the physical address. And the computer system, the kernel, the OS, and the hardware work together to give you this mapping. Basically, given the virtual address, where is my physical address? Right? And this unit called the memory management unit, this is like the terminology that you see again and again and again in the area of address translation. It manages the translation between virtual address to a physical address. We will learn how this is done today. The first benefit is with this mapping between virtual address and physical address, each application only have to worry about their own virtual address. Any question about the first benefit? If I'm running a program in C, I only have to worry about the address that I allocate. Why is that the case? Each application has their own virtual space. Whenever you call malloc, the OS gives you, there you go, that's a space you can use. Feel free to use it. Everything inside there is your own. No one will be able to use it. Any questions so far? So the second question is, I told you we can have unlimited memory. So how is that possible? So technically this is limited, but it's a lot bigger, right? The concept is this: you have DRAM and you have the hard drive. So what's the size of your hard drive on your laptop these days? How big is your hard drive or SSD? Then 1 terabyte. Yep. And how big is your DRAM? 16 gigabytes. So basically, you now realize your DRAM is a lot smaller, right? So let's say you want to allocate a lot of memory. What the computer actually do is it go through all this allocated space and figure out, okay, that data, you haven't used it for a long time. I'm gonna kick that out to the hard drive. There's an area in the hard drive we call a swap space, where it store all these data. And the virtual address that maps to these swap space, basically they will not be pointing to DRAM. It will say, okay, you need to go and find that data inside the swap space, which means that you virtually you can use the hard drive as your DRAM. What's the downside of this? What is the downside of the case where a lot of my data are in the swap space? What can happen? So what will happen if I need to access my pointer from the hard drive instead of DRAM? Yes, every single thing becomes slow. So you might have realized sometime when you have 30 Chrome tabs opening at the same time, your computer somehow got really slow. This is actually why. You run out of DRAM, right? You run out of memory. That becomes a meme, right? If someone suddenly turns really slow because you run out of memory on your brain, this is the case. A lot of the data get kicked out to the swap space, and every time you have to access it, it's taking so long. The program is not crashing; it's just super slow. How slower? Thousands of times slower. One terminology I need you to know is something called a page. Right? A page is essentially it's a range of address. Typically, if you look at CPU, that's 4 kilobyte range of space. This is similar to cache block. When I said like a cache block is 64 bytes, over here a page is 4 kilobytes. This number can change based on the architecture. Right now, if you look at the CPU, the Intel CPU, these are 4 kilobytes. It can be much larger based on the design. And to get the physical address, we will rely on whatever we call this page table structure. What is a table? A table is basically it's an area you can store a lot of mapping, right? So it maps the location of your virtual address to the physical page. This is used to determine the physical address given the virtual address. The page table is organized in a tree-like structure, and I'm going to explain why. All of these page tables are stored inside your DRAM. So this is really important. In an Intel x86 processor you have nowadays, you have 4 levels of the page table, where the root is actually called the CR3 register. The value of the CR3 register points to the first level. I'm going to slowly explain how the translation is done. Basically, you use the virtual address plus whatever is in the page table structure to point to the second level. Once you're in the second level, you also use the virtual address again with the data to the second level to point to the third level. This is why it's a tree-like structure. This process is called page walk. So let's go through some examples of address translation. Let's assume you have 2 levels of the page table. Each page table is containing 1,000 different entries. You have 32-bit address space. And given these virtual address, you can tell what is my physical address. So here is the page walk example. So I'm gonna animate the example. I initially I have a slide that kind of like I would draw it manually, but I ended up drawing everything here and have an animation so that it is more clear. So here's a page walk using that example. You have the virtual address like this, right? It starts from the virtual address. This is 32 bits. This is bit 0. This is bit 31. If you have 4 kilobyte page, right? 4 kilobyte page. I want to be able to tell each exact byte inside these 4 kilobyte pages using what we call the page offset. So how many bits do I have to have inside the page offset so that I can tell all the unique location in my 4 kilobyte pages? How many bits do I have? So I have 4,096 different unique locations. How many bits do I need to represent all those 4,096 different locations? Then close my office door, I'll be right back. How do I get that number? This is the same thing as the cache index. If you have 16 sets, you need 2 to the 4, which is 16 unique locations. So if I have 4,096 different locations of bytes, how big should my page offset be? Am I going too fast? Like, are there any questions that you have? Twelve bits. The reason why it's 12 bits is log of 4 kilobytes, which is 12. Right? So you know that's bit 11. So bit 0 is for the page offset. So for each of these index 1 and 2, this has to cover 1,024 entries. So how many bits do I need for each level? How many bits do I need? What's log of 1024? 10, right? So you know this is going to be 12 to bit That's 21, and this is bit 22 to bit 31. Based on that, what I just told you earlier is there's a register called CR3 register that stores a value, right? Let's say the value is 0x, I don't know, 0x14. What happened here is it would point to the location of your page table right at the beginning, right at the beginning. If it's 0x14, it knows that the first level of the page table is at 0x14. Then what you need to do is, if you want to do the page walk, you take index 2. There are 10 bits there, right? And let's say this index 2 is a bunch of 0 followed by 101, which is basically number 5. What do we do there? What is the address that I need to look? If this has 1024 entry, and each entry is 32 bit long. If I have 1024 entries, I want to look at the 5th entry. Each entry is 32 bits long. So what address am I looking at? What address am I looking at? So this is the 0 entry, the 1st entry, the 2nd entry, 3rd entry. This is the one I want to look at, right? This address is essentially 0x. Because I know that I need that space. This address is 0x14 plus 5 multiplied by 4. Why is 5 multiplied by 4? Each entry is 4 bytes because each entry is 32 bits. The 5th entry will then become 5 multiplied by 4. So you add 20 to 0x14, and that is the address that I need to look at. Then from there, in this PTE, what you see is there'll be a part called physical frame number, and then the metadata. These are things like, can I access this page? Is it supervisor versus user? Is it read or write? So these tell you who owns the page and can I access them. The physical frame number, this part is the important part. It tells you the location of this second level page table. Let's assume this location is 0x10,000. And let's assume your index right here is index 10. What is the address of my level 1 page table entry? I did the last level for you. Can you tell me this level? What is the address of the level 1 PTE inside Jira? If the entry is index 1 is 10, I want the 10th entry. It's going to be what plus what? The base is at this address, and I want to move 10 entry from the base. So what is the address? Yes. So I assume you missed 10, but basically this address is 0x1000 plus 40, right? 10 multiplied by 4. This 40 is basically 0x, if I'm not mistaken, is 32 plus 8. 32 plus 8 is 18. So this address is 0x1018, 1080. in hexadecimal number. From there, it looks like this. This entry would have what we call the physical page number, and then again metadata bit, which have some information about who can access what, has this been accessed the last time, when, and the part that you want is you want the physical page number here. Your physical address is essentially the physical page number and the page offset from here. This offset goes in here. The physical page number from here goes in here. You append them together and you have the physical address. Any question so far? Any questions so far? Because I can guarantee this will go on to your exam. If this sentence can wake you up, and let me know what is your question, because I want to make sure you got the idea. And it's okay if you are like, I'm confused. I'm gonna try to digest this a bit and come to office hour or send me questions in the email. Let me know later, that is fine. What is 0x14? Over here, it's assumption that CR3 registers has 0x14. It can be any number. It can be any number. Basically, CR3 points to the root. Okay, so that's another great question. So is it clear on what is 0x14? It's just the number I make up. Whatever CR3 is pointing at is the base of the first level. Right now, if I say 0x14 is CR3, so that goes to the base. What does the PC do when it runs out of swap space? It crashes. That's what happened. That's when the computer crashed. So basically, the allocation will be like, okay, I run out of memory. I can't do anything. So bye. These days you are not likely to run into that. You are more likely to run into the point where you are like, your computer is too slow, I can't do anything, I still have swap space, but it's useless. So it might kill some processes to free up the space. It might kill itself and crash, depending on how you write the OS. Whether the kernel determine what will happen. Whether the kernel determine what will happen. All right, so let's go to a realistic scenario in a 64-bit x86. I'm not saying this is not realistic, but this was old. The last time we have 32-bit x86 was about 10 something, or no, 15 years ago, I think. With the 64-bit machine that you have nowadays, the offset, again, we use 4 kilobyte pages, so the offset is the same. Then it breaks down into now 4 levels. Each level has its own index. So the index level 4 we use to access the first level of the page table entry. Then the same process. This is essentially the exact same process, but you do it 4 times. So once you are at this point, the PT, as I said, consists of, again, physical frame number. This gives you the next level, and you basically use the index 1 to point to this. This point to your DRAM using the physical address. Any questions so far? With more levels, you just need to go through this more time. Any questions so far? All right, so now that you know that, okay, with more levels, you cover more range of addresses, but there are performance overhead, right? If you have 4 levels of the page table, these page tables are in DRAM. What does it mean? What does it mean if my page table is in DRAM and I need to go 4 levels? to get my physical address. This is slow because you need to go to DRAM 4 times just to get to know where your data is. Think of it this way. Let's say I have a house, right? And I tell you the address of my house is easy. You go to that address. Then if I'm going to throw you and say, okay, if you want to go to my house, go to this address first. That address tells me the location of the second address, then tell me the location of the third address, which tell me the location of the fourth address, which then tell me my address. You're gonna take a lot more time to get to where I am, right? This is the same thing. So the problem that we have is you cannot access DRAM to get your data without knowing the physical address. So that's a great question. Does it go through each level in one cycle? Actually not, because each level you have to go through, you access DRAM. So DRAM these days is ranging the access time between like 10 nanoseconds to around 50 nanoseconds. If you have 3.3 gigahertz processor, 3 cycles means 1 nanosecond. So if you have to access that in 10 nanoseconds, how many cycles is that? 3 multiplied by 10, 30 cycles to go to one level. Assuming that that's a minimal time. When we go through the DRAM lecture, you know that sometimes it actually takes a lot more time to get there. It can take hundreds of cycles to go through one level. So if you take hundreds of cycles to go through one level, going through 4 levels is like 500 cycles just to know where your data is. So you have to add one more DRAM access. Why do you have too many levels of the page table? So let's say you have a 32-bit machine with two level. You have 32-bit machine. How big can your DRAM be? How many unique address can you get from 32 bits? 2 to the 32, right? What is 2 to the 32? In 2 to the 10 is 1000. 2 to the 20 is 1 million. 2 to the 30 is 1000 multiplied by 1 million. That's 1 gigabyte. 2 to the 32 is 4 gigabytes. How many of your machine only support 4 gigabytes of DRAM? How many gigabytes of DRAM do you have these days? More than 4, for sure. I'm pretty sure none of your machine is 4 gigabytes, has 4 gigabytes DRAM, right? Which means that you need a wider range for your address. That's why we have the 64-bit machine. So 64-bit machine, you can kind of support up to basically 2 to the 64. My brain freeze, so I'm not gonna calculate that number, but you can support up to 2 to the 64. But the problem over there. So that's a great question. So even by different RAM stick, right? They have the same page table structure. They would assume this thing goes based on your ISA. The ISA tells you how many levels of the page table you have. So that goes based on your Intel processor or your AMD processor or your GPU. It tells, okay, it goes through this many level of the page table, and the OS will implement it. You can implement different techniques in the OS as well. You can modify this a little bit through the kernel and through the hardware. So it is not tied to the size of your DRAM. More level, it means you can support bigger DRAM. So over here, when you have 64-bit machines, it means you can support up to 2 to the 64 unique addresses, which by that point, we all hope that's enough, right? I hope that's enough. Because 2 to the 40 is terabytes, 2 to the 50 is petabytes, Right now, I'm not sure we can even go to the 60 within the next 10 years. Uh, at least with with the RAM technology. So when you buy different DRAM sticks with different sizes, they all have the same structure. They have four levels on the page table. The OS tells you where to map it. The OS will create this page table structure based on the ISA specification, and then the OS and the hardware kind of work together to actually translate your address. But yeah, all these are great questions. And it does it answer your questions, both Champ and Brandon? Okay. All right. So that's the first problem. The second problem that you might have forgot. What do we have? We have the cache. We have the cache. We don't want to go to DRAM because DRAM is slow, so we want to use the cache. The second problem, which we'll discuss why this happens, but in a lot of cases, if you don't do anything with the translation, you cannot access the cache until you know the physical address. We'll go through the reason why. So bear with me for now. We'll go through each of these two problems one at a time. One at a time. So let's go through the first problem. You cannot access DRAM without knowing the physical address. What can be the solution? You have that solution already. What did we learn last in the last class? What is the topic on Monday? What is the topic that we learned on Monday? This Monday. I'm kind of surprised at how long does it take for you to respond to that question. On Monday, we were learning caching, right? We learned caching, which is, hey, we can have this small memory to store frequently used things. So the idea is you can cache them. You build another separate cache to store this translation data. The reason why they call it translation Lookaside buffer is we want to have a buffer that are fast, and these buffers store translation data, right? So the idea is this: if you need to access the address that are common, right? Let's say you go through an array, you can cache the translation so that you can look up the physical address given the virtual address. And similar to the cache, right? Similar to the cache, there are layers of this structure. There can be L1 TLB followed by L2 TLB. And in the end, if your physical address that you want to look up is not in this TLB, then you go do page walk, right? So any questions so far before I move on to what goes into the TLB? Any questions so far? So here's the structure. What do I typically have in my cache? I have the data. I have the tab. Okay, as simple as that. So what can I use as a tag? You have the virtual address, which contain the page offset, and what we call the virtual page number. And the page offset. On the physical address side, you have the page offset and the physical page number. These page offsets are the same. these page offsets are the same exact number from virtual address to the physical address. So my question is, what do you need to put in the tag and what goes into the data? What is the key? What is the data in my map? So what goes into the tag? What do I search? What is the key? I have VA, I want EA. So what should I put? Which one is unique in the virtual address so that I can use it to tell the physical address? Exactly, yes. So you put in the virtual page number here, and you put in the physical page number here. Because you know the page offset is the same, there's no need to put in the page offset. Over here, each entry contains the virtual page number, and you get the physical page number back. So for this entry, how much data do they cover? So let's say the page offset is 12 bits, right? One entry cover 2 to the 12, which is 4 kilobytes of data. If you access anything within those 4 kilobytes, this one entry can give you the physical address. Any questions so far before we go to our next solution? So our next solution is called the page walk cache. The page walk cache is also exists on your CPU. The idea is because the page table structure is in a tree. It's something like something like this, right? Which means that in the TLB basically make you jump from here to here, right? This is the TLB. One thing you can do is, well, if you don't want to jump all the way down, you can kind of jump from here down to here. Page walk cache. You don't jump all the way to the leaf because there's not a lot of common path. You can jump through just the common path. We call this page walk cache. The idea is cache partial translation data. For each page table structure, you store common path, common branch of the tree. The benefit here is to provide much higher coverage, but the downside is you need to do the page walk for the last level or the last two levels. So the page walk cache structure, as I said earlier, is something like this. Here you have the full level of the page table, right? So the page walk cache will actually have the virtual page number from here. Instead of giving the physical page number, which is the last level, it doesn't because you don't go down to the last level. You go just to this path. So you can get physical frame number for so this is level 4, level 3, level 2, and level 1. So you get from level 4 down to level 2 in one cycle. Then you from level 2 you spend one more hop to DRAM to get to level 1 so that you know the physical address. So as you can see here, it's still fast enough. Actually, it's quite a bit faster. Right? But by this point, because you realize you have to access DRAM, HWalk is still expensive. So you can use the combination of these solutions. My bad, two solutions, the TLB and the HWalk cache. And there are so many other ideas that you can do and kind of address the overhead of translation. There's optimization on the CPU. You can use large page. We will discuss this right now. Segmentation, we're not going to discuss it. I can briefly talk about one of the work I've done with the student at CMU on how to get better at doing segmentation using hardware. You can make a larger TLB. You can also do this on the GPU. So this topic is still important. It nowadays move to cloud, and I'll tell you why is that really important. Before we go through like the real world scenario, let's stick with the second problem. In modern design, you cannot access the cache without knowing the physical address. The reason I'm gonna tell you is pretty unique. So when you talk about caching, right, there's the index bit and there's a tag bit. And I never mentioned that, hey, you got the virtual address. You got the virtual address. You start with the virtual address. So what is my option if I know I can have virtual address and can have physical address? What are my options for the index and tag bits? There are 4 different options. If you do a full permutation of this, you can have index coming from virtual or physical, and so does the tag. So there are 4 choices. You have physically indexed, which means I use physical address for the index bit and physical address for the tag bit. Physical address for index bit, virtual address for the tag bit, virtual address for the index bit, physical address for the tag bit. Lastly, virtual address for everything. Virtual address for everything. There are trade-offs with all these 4 different choices. And before we go into these in detail, let's take a quick break. Let's take a quick break. We'll meet at 1 p.m. Please go get coffee. We will tell you what is the downside of each of these techniques and what is common that we use in the CPU nowadays. All right. Also, if you have any questions about the things we've been covered so far, the page table structure, page walk, TLB, and the page walk cache, let me know because I went a little bit faster. I assume that most of you took my system skill and file processing, and those of you who didn't take the system skill and file processing, I assume the earlier version of this also covered this topic as well. If not, please come with questions so I can explain how this is done. I don't mind. Right? I just don't want to bore you to death by saying the same thing again and again. So let's take a break. We'll meet back at 1 o'clock. Is that okay? All right, I'm back with some coffee. Yes. Okay, are you guys back? Okay, so there are basically the issue with why we cannot access the cache, right? The cache is fast, and we need to be able to access them. The issue is it comes from the fact that we might need to use the physical address for some of these things. We might need to use the physical address for some of these things because of two problems. The first problem that we can run into is called the homonym problem. Two programs have the same virtual address. Yay. What do they mean? There are two different programs. They map to different physical address because they are two different programs. This is called homonyms. So you need to be able to tell that these are two unique virtual address. These are two unique virtual address. What will happen if the tag use virtual address? What will happen if I use the virtual address for my tag? Can someone tell me what will happen? What will happen if the tags are the same? Because I told you that the tags are the same because the virtual address is the same. No matter what you do, you have the same tag. No matter what you do, you have the same tag. So whatever tag is in the cache, is there a way for me to tell, is this on my application one or is this on my application two? Is there a way to tell this? Yes or no? Is I'm boiling this down to just yes and no question. So I'm waiting for you to type in yes or no. Is there a way for me to tell that the data in my cache is from which virtual address if I use the virtual address for my tag? No, yes, you are correct. It's impossible. I cannot tell. Right? Which means that there's a chance that you fetch someone else's data by accident. Right? So what is the bad thing that can happen if you fetch someone else's data? A lot. You got the wrong data. Someone else data is visible by some other program. You can easily hack that program because you just expose the data. So everyone is on the same page with the homonym problem. Before we move on to the second problem called synonym problem. This is the inverse of homonym. You have one physical address, but you have two virtual addresses. Why can this happen? Why can this happen? You might have shared data, right? You share the physical address. The two programs use different pointers, just happen to share the same data. This is called synonym problem, which means that somehow you need to tell the differences between the two. Oh, actually, never mind, my bad. This is copy and paste stuff. Don't worry about this part. Synonym problem cannot be solved by the tag. So we will not, this is a graduate level. I just want to introduce this problem to you. But it's possible you have data sharing to virtual addresses mapped to the same physical address. So let's come back to the question of should the index and the tag be in virtual address or physical address, right? which one of these four will have homonym problem? One virtual address somehow mapped to physical address. Which one of these four will have the homonym problem? The VIPT is actually will not have the homonym problem because you use physical address for the tag. There are two physical address already, so you can tell that this is the tag for address 1, this is the tag for address 2, right? So if you use virtual address for the tag, VIVT or PIVT, these will run into the homonym problems. Are you all with me? Are you all with me so far? Yes, no? So right now, PIPT and VIPT are okay. Right? PIPT and VIPT are okay. Are you all with me on that? Basically, you want to use physical address for the tag. You want to use physical address for the tag. Any questions so far before we move on to which one of these two are the best? All right, so assume no one have any questions. What is the issue with PIPT? It means that you need physical address for everything. You use physical address for the index, physical address for the tag, right? So this is the process. You have virtual address. You need physical address for both the index and the tag, which means that you have the virtual address. You then check the TLB. If the TLB doesn't give you the physical address, you do page walk. So this is the cache blocks, which will then use to compare the tag. Basically, you start from the virtual address, you check the TLB to get the physical address. If it's not there, do the page walk, get the physical address. Use the physical address to go to the set to access that set in the cache. Then you compare all the tags. What about VIVT? Again, as I said, VIVT runs into the homonym problem, so we're gonna skip this part. But a quick thing is that these days there are more and more works that discuss that, hey, maybe this is not too bad. There are ways to prevent this from happening. We will not cover this, but if you're curious about these ideas, let me know. I can go further into some of these ideas. Then let's discuss the solution to the problem. VIPT. VIPT. What is VIPT? Virtually indexed, physically tagged. We use virtual address for the index. You use physical address for the tag. Why is this okay? We can use physical address again to check the tag, right? This is okay because this is unique. So there's no problem here. Benefit is you can then overlap that lookup with the TLB lookup. So here's the process. You start with the virtual address, both the TLB and the cache. So you use the index to get the cache, and you use the virtual address to get the physical address. Once you have the physical address, you get the cache set. So these, you basically compare the tag which means that while you are trying to get your physical address, the index bit is going ahead to get my cache set. The difference between VIPT and PIPT is you don't have to wait until you get the physical address to use it as the index bit to get your cache set. So these part of the process, the part I'm gonna circle, this part of the process can be done in parallel with the TLB lookup. Any questions so far? Anyone have any questions so far on why VIPT is more desirable? All right. So the downside, obviously, if you have a TLB miss, you still have to do the page walk. So you might have now realized that avoiding page walk is really important. The next issue is what we call page fault, right? So you have the virtual address that can map to something bigger than DRAM. Some of them are stored in the hard drive or the SSD, right? So what if we want to access that page? What if we want to access that page? Basically, what you do is you do the page walk. The page walk will tell you it's a fault. It's called page fault. Page fault means that, hey, your page is not in DRAM. You need to go and find where it is, right? So to remedy this, basically the OS will go to the storage system and it takes a really long time to get your data. Any questions about this? Any questions about this process? Basically, you go and search your swap space for that page. Once you got the page, put it back into DRAM, which means that when you put it back into DRAM, it means your memory is full. So there is also a policy to replace the page, right? Similar to the cache. You can replace a page from your DRAM and hard drive, right? This area again is called swap space, and there's a policy that migrate the page that's not likely to be accessed again. The how part is related to how basically we need a way to tell how many times you access each of the pages and what is the information that the OS will know. This is covered in the OS class. So if you're curious, let me know. Toward the end of this class, I'm going to talk about one of my work that take a look into, can we do a better policy? Is there a way for the hardware to help and get a better policy? Dealing with synonym in VIPT is basically two virtual address mapped to one physical address. There are multiple possible solutions. These won't go on to your exam because this is graduate level techniques. Mainly we'll do what the OS right now can do. The technique is called page coloring. You restricted where each process pages can go. Again, not going to go to your exam, so I'm gonna go through this quickly. If you're curious, let me know. I can expand this during office hour or after this class. The last thing we need to cover is the third benefit. The third benefit. You have memory protection. Why is that the case? The page table entry, you remember our page table, right? Level 1, level 2. These entry has bits that tell who can access the page. Is it read only? Is it owned by the kernel or is it owned by any user? Who owns the page? What process owns the page? Can I modify that? All those bits inside the page table, if there's any violation, you get an exception. So when you run a program, you try to access some location that's not legal for you to access, export, exception. So these are the things that are common when you mishandle your virtual address. If you mishandle your virtual address, somehow your virtual address mapped to some random location, you will get an exception. These bits can include things like address space ID. This is unique to the process. You can have read-write, read-only bits, user versus supervisor bits. All right. Any questions about this before I kind of like wrap everything up from Monday and today? Okay, so let's do this. Let's assume these are the whole thing that we talk about from Monday and today. And let's say I want to do this. I want to say I equal a of 0 on your program. What is a of 0? Is that virtual address or physical address? What is a of 0? If I have that line in C, is a of 0 virtual address or physical address? Virtual address. So this is virtual address. Let's assume two levels of the page table. This virtual address is broken down to three chunks. This is the page offset. This is the index 1 and index 2, right? Let's call this number A, B, and C. Just for the sake of sanity, we just call index 1 A, index 2 B, page offset C. Somehow I want to get the physical address. Somehow I want to get the physical address, and I will call the page offset E, D, and E. So this is page offset. This is page number. Right, D and E. Everyone is with me so far. I'm just defining different number and defining different variables which I'm going to use in this example. In the cache, let's assume there's a L1 cache and the L2 cache. And one thing I'm going to change the color of everything physical. I'm going to change the color of everything that's physical to blue. So you have the physical address that consists of the physical page number and the page offset. We call this D and E. So your DRAM is now in blue. Everything physical is in blue color. Everyone with me so far? Virtual related thing, white. Any physical related thing, blue. What is our first step given the virtual address? If I want to access that data, if I want to access A0, what is the first thing I need to do? So the first thing is I'm gonna have my index bit. find the index bit inside the virtual address, right? With the index bit, what do I get in the L1 cache? What do I get? I get the cache set. I know the set that I want to access. Right? I get the cache set. Let's say this is set say 4. I'm gonna go to set number 4 because the index bit is what value? What's the value of my index bit if I go to set number 4? If I want to access set 4 in the cache, what is my index bits? What value should it have? The index bit should have the value 4. The index bit corresponds to the set ID that you are accessing. So set 4 corresponds to index 4. I have the index bit. How do I get the tab? How do I get the tab? What do I have to do? Do I use the physical address for the tag or virtual address for the tag? EIPT, physically tag. So I need what for the tag? Virtual address or physical address? Or no one is here? I'm not sure if I can get the response if no one is here. That's the problem. Someone say something. Or should I repeat the questions? Or am I going too fast? Or are you confused or something? I need to get some feedback from you so I know how to proceed. All right, so I'm gonna keep going because no one say anything. I'm not sure if I'm going too fast or too slow or anything. I'll keep going. If you have a question, type it in or let me know after you watch the video that I posted. But basically, if you want to get the tag, you need the physical address. To get the physical address, you need to translate from virtual address to the physical address. So you have virtual address in coming in here. The first thing you search is the TLB. So you put the virtual address in here, search the TLB. If you find that entry, you will get your physical address. I'm gonna use blue color here. You got your physical address if TLB hit. You get the physical address. You use the tag to find your hash block. If you cannot find the virtual address from the TLB, then miss. If the TLB miss, you start doing the page walk. So from here, this is where the CR3 register is. You use index 1, which is the value A, right? A from here. To find the entry, page table entry, that correspond to the pointer that points to the second level of the page table, which you then use the value b, okay, to get your page table entry. From here, you will have the physical page number and the page offset that you can use. This becomes your physical address. This physical address is used to compare the tag. If yes, your data is returned to here. If tag match. If not, you then move on to if miss in the L1 cache. You then move to find your second level of the cache. If it hits, then you go here. If you miss, then you go to use a physical address to access your data from DRAM. So this is everything. Given your virtual address, given your pointer in C, this is how everything works. This is how you can get your data from DRAM or the cache or the L1 cache. This is also how you get the physical address. Any questions about this figure? Because these summarize what we learned on Monday and today. Okay, so now that I talk about the textbook virtual address translation, I want to extend it a little bit more on, okay, what happened in the real world nowadays. Can someone tell me what are the common applications people love to look at these days? Assuming that some of you are still with me, what are the common applications that you want to use, learn, or what is the trendy topics right now? Soon, I guess. And what I'm leading to is something like AI, right? Machine learning, IoT, right? Things like these applications that people love to look at. How much data do they consume? Oh, crap. Big data. Oh, database. Or whatever you be called data science. You consume a lot of data. Right? So the virtual memory that support these applications has to be designed for the application, which also means that you need to have a good virtual machine or container infrastructure to support this. So right now, let's assume that these applications utilize either virtual machine or container and run in the cloud. Because it requires a lot of data, you don't want to buy like entire machine for yourself. Even when you buy the entire machine for yourself, you need to figure out how are you going to deal with virtual memory. But one of the important things in virtual machine, how many of you use virtual machine and realize it's so slow? How many of you used a virtual machine before or a container? How much slower do you feel? Like compared to your own machine, how much slower? Is it 1x, 2x, thousand of x? Yeah, it's super slow, right? One of the main downside of virtual machine is this. Let's consider the problem of address translation. We will call right now the virtual machine, I'll call it the client, basically where you run your program. And these are run on your host machine. It's a terminology, client and host, right? The host is where you have the program that run the virtual machine. The client is whatever is inside the virtual machine. Where do you plug in DRAM? Is it inside the client or is it inside the host? With the physical DRAM, the DRAM stick that you buy, it belongs to whom? Who owns DRAM? Is it the client or is it the host? The physical DRAM. The host owns DRAM, right? So virtual machine is a program, right? VirtualBox is a program. Docker is even it's so the same thing. It's a program running on the host machine. They run on the host machine. Everyone agrees on this, right? It runs on the host machine. What happened to the pointer inside the virtual machine? We call this client virtual address. We call it client virtual address. I'm asking this question because this is a leading question to the next slide. How do you translate from client virtual address to the host physical address? Host owns DRAM, so the physical address to get to that particular value, particular cell in DRAM, the DRAM stick that you buy, you need the host physical address, right? In each virtual machine, it runs its own operating system, right? It has its own totally isolated environment. It runs its own Linux, Ubuntu, even Windows that you have on the virtual machine. So the client virtual address has to be translated to the client physical address. Everyone agrees on this, right? Any questions so far? So you need to somehow get the client physical address. If you run 64-bit Ubuntu, how many levels is that? If you use 64-bit Ubuntu, how many levels do you have in your page table structure? It's 4 levels, right? Are you with me so far? Because it seems that everyone is quiet. Then, when you have the client physical address, somehow the actual client physical address is the host virtual address. Because this is a program running on the host, right? That's the virtual address. Then from the host virtual address, you need to translate again into the host physical address, right? So this is what happened. I'll call client virtual address CVA. I'll call each level is client page table level 1, 2, 3, and 4. Host virtual address, host physical address, HVA and HPA. So you start with CVA, client virtual address. What's the first thing I do? I do translation. The first thing I have to do is I go to client page table level 4, right? What is this? This is client physical address. So when you have the client physical address, this is essentially the same as host virtual address. right? It's the same thing. This page table level 4 is the client physical address, which is also the host virtual address. So you go to host page table level 4, host page table level 3, host page table level 2, and host page table level 1. Then when you add host page table level 1, host physical address, to get to where the page table level 4 is, you need these many accesses. What's next? Once you are at page table level 4, the next step is you have the client page table level 3. This is the same as client physical address, which is the same as host virtual address. Which means you have to go to the same structure again, host page table level 4, host page table level 3, etc., etc. In total, to get from client virtual address to host physical address to get your data, these incur 24 DRAM accesses. 24. Now, do you see why this is 1,000 times slower? It's 24 DRAM accesses. Any questions so far? Any questions so far about why running things on a virtual machine is slow? Very slow. Any questions on this? Because if you have no question on this, or if you're still trying to process the information here, you can let me know later, or you can ask me now. But I'm gonna start to move on to what about big data? Okay, so let's just assume that you buy the idea of the one of the reason, is not every single reason. One of the reasons why virtual machines become slow is this: one memory access, 24 access to DRAM. There are actually a lot of techniques that reduce from 24 to 4 or 5 level of accesses, but still not perfect. So the second concept that we start to gather some interest is our huge page. This is relevant when you have data that has a lot of memory or requires a lot of memory. These database application, these AI and machine learning. So let's say you have 512 entry of TLB and the page size is 4 kilobytes. How big can the TLB cover? Can someone tell me how big can a TLB cover if you have 512 entry TLB and each entry covers 4 kilobytes? It's 2 megabytes, right? How many programs only have a working set that consists of 2 megabytes of data that are realistic? Can you write a program that only covers the 2 megabytes of data and basically that's what they want to use? In most cases, that's not true, right? So one of the things you can ask is, well, what if you programming one homework? Yes, something pretty basic, right? It will fit within 2 megabytes. But if you do something more realistic, you load one image, for example, that's already more than 2 megabytes, right? So what if you increase the page size? The same 512 entry TLB, how much does it cover if I have 2 megabyte pages? Can someone do the multiplication and tell me the size? 24 gigabytes. Right? So what is the downside of this? This is what we call fragmentation problem. Let's say you do malloc, something. How big is this thing when you call malloc? It can be less than 1 megabyte, right, as well, right? Sometimes you want to allocate 1,000 entry, 10,000 entry in your array. So sometimes it's less than 1 megabyte. So if you assume that every page is 2 megabytes, what can happen is your DRAM will look fragmented. So this is 2 megabytes. Each block here is 2 megabyte chunks, right? But you might have the shaded area, which are the one that are actually allocated. And it looks really fragmented like this. Because you're not using the entire 2 megabytes. Right? There are some pages that doesn't use the whole thing. So over here, you lose DRAM. It's literally you lose, say, you have 16 gigabyte of DRAM. At some point, you run out of DRAM faster than you expected if you use large page. So these days, you can enable Linux THP, which kind of combine both small and large page sizes, where it contains the promotion and demotion policy. Promotion means that I have a bunch of 4 kilobyte pages. I'm going to promote them into 2 megabytes. I'm going to combine them. Demotion means that I'm going to break them apart from 2 megabyte pages back to 4 kilobyte pages. The problem of doing this, which I'm going to follow up from the work that I just presented this month, I think 2 weeks ago, in a conference, is there's actually quite a lot of cost in doing this. If you go look at Redis and a lot of a lot of database structure like MongoDB, CouchDB, and a bunch of other big data platforms, there's actually a lot of discussion about you should not use this. The reason behind that is things like fragmentation that we have earlier, right? There's also some fairness issue. Who get to use 2 megabyte pages and who get to use small pages? There's also an issue with replacement policy. How are we going to deal with the case where we can evict some data from your DRAM? So we'll follow this up on next Monday. In the meantime, before we are done, quick reminder, there's a checkpoint next Monday. The checkpoint, as I said, I want to make sure you start to look into what is pipelining. How are you going to pipeline it? I don't want you to have a fully functional pipeline, but let's at least make it such that you can ask me questions on where to go next after you have the pipeline registered. All right? Is that an okay checkpoint? And the next week, I'm going to start with some review on what we covered so far, followed by I'm going to introduce one work. Actually, it might be 1 or 2 works on virtual memory. There's one work that tries to address a problem where you have virtual machine running, and I don't want to do 24 page walk, 24 DRAM accesses for the page walk. The second work is more along the line of if I use huge page in Linux THP, how can I get better at using the page in a better way? So how many of you know Frank? So he was kind of helping with the second project, actually, on how to manage the page better. So if you're curious, you can check with him as well. I'm kind of talk to him before before he finished his degree about like maybe extending that work for a journal submission, and we'll see how it goes. So I'm gonna talk a little bit about that work and maybe some future direction on that particular work, and hopefully you get a little bit more insight, I guess, into not just how virtual memory works, but how does it actually work with the modern day system, right? With the system where you run things in the cloud, a system where you run things on the GPU, and somehow things get really slow. So these are some of the things that happen. The GPU part, I'm gonna cover this after my GPU lecture. So that's toward the end of the semester. But I need to first teach you how GPU works. Next week, besides the checkpoint, I'm gonna start to dive into DRAM. I want you to be able to tell when you buy DRAM, that RAM stick that you buy. You see the chips, right? The black things over there. And you see a lot of connection, the copper looking thing. I want you to be able to tell how that works. How can I get more performance with different DRAM technology? So hopefully you are slightly excited about this. I know that a lot of you are not going to dive into like the hardware topics, but at least I hope these new things that you learn, and I hope that you can kind of like combine some of the things you learn here for whatever you program in the future. Again, the content we covered this week is so important for your performance because you want to make your program as cache friendly as possible. So please keep that in mind. Please keep that in mind when you want to improve the performance of your program. Any question before we leave today? That's it for today's lecture, actually. Any question before we leave today, except for I forgot to post the PDF and the video. All right. So if no one have any questions, you can sign off now. If you have question and you're still typing, I'll wait until 2 o'clock. Basically, I'm gonna wait until 2 o'clock and